The general theory of cyclic harmonic curves given by Robert Moritz is surprisingly short. It is 11 pages. Here, I read through it, highlighting maybe some information that wasn't around in 1921 when this was published. This video could get long, so here is the too long didn't read until I say otherwise. The general theory of cyclic harmonic curves by Robert Moritz can be found at this website right here. The equipment that he uses, the geometric equipment he uses, is this right here. I have reproduced it right here. There's also this applet here, T for time, Q, P. So many options, okay? And they will create this curve, a curve. What is that curve? They are the cyclic harmonic curves. During my read-through, I will bring up OEIS, why my old first favorite Russian mathematician has now moved to number 2. Right? He was my first favorite because of that formula right there, that constant that bears his name. My new number 1 is Pafnuty Chebyshev. That's how I'm going to say Chebyshev. This is him. And why? Well, the Chebyshev polynomials. Well, how does that relate to this? Here's HP prime software or any CAS software. Take the absolute values of the coefficients of the Chebyshev T. Here I'll use 9. It generates this list. This list can also be found right here, which is also right here. He never mentions Chebyshev, and Chebyshev never mentions him. Another great work by the same author, if you enjoy math quotes, he has compiled many math quotes. It took him over 10 years. I enjoy 12, 13. The last thing I do in this video is construct an alternate method for the cyclic harmonic curves, which will be the focus of the second video. Should be about the last 1 minute of this video. This concludes the no spoiler, and now I go to the reading. The General Theory of Cyclic Harmonic Curves by Robert Moritz in 1921. Here he gives the initial definition. He calls the cyclic harmonic motion may appropriately be defined as motion resulting from the composition of simple harmonic motion in a straight line with uniform rotary motion about a fixed point in this line. The locus of the resultant motion is a cyclic harmonic curve. The equation that can give the cyclic harmonic curve is right here, right there. Rho equals alpha cosine pt plus k, where alpha is the amplitude of the vibration. Theta will be given as qt. To investigate his construction, let's read through his definitions. It says that let OA represent the initial line. O is the pole from O to A. Lay off OC, that is equal to K, and with C as the center and the radius equal to alpha. Describe a circle of reference, thus the simple harmonic motion. Select any convenient unit of angular measure and construct angles ACR and AOB equal to PT and QT respectively. T being an arbitrary, any arbitrary chosen integer. Okay, from R, draw RS perpendicular to OA, and from O as the center and OS as the radius, OS as the radius, describe the arc SP cutting OB and P. Looking back at my notes now, I said, oh, this is where I said, there we go. So I said, oh, the simple harmonic motion is represented by that circle. So figures, then he says, by the way, figures 2, 3, 4, 5 show methods of construction. So now I will recreate those same methods. This is very close to his first construction. How a person could read this is that there's two radii, this one right here, which is alpha, and this one, which is rho. When they're in position 1, they lie on the same position. And then as they advance a unit, one single unit, this is where they will lie. And then another unit, and so on, and trace out this entire curve. You see here, that's kind of like 2, there's 3, there's 3, let's see, 4, and then finally you can see that 5, so now we've recreated his first initial figure 2. These were the first values that I used. These are much more of his general form. On to the next. Okay, for here, I could see that these settings here are 1, Q is 1, P is 2, K is 1, A is 1. Let me just change K to 0, and it should match figure 3. And there's, we could show it like that, or it could be understood that it could just be in motion That's good. So there's figure 3. To reconstruct figure 4, I'm going to take k from 0 to negative 0.5. That is reconstructed 4. And actually, I just want to turn this off. I'm going to reconstruct figure 5. He notes that this is a very special case. Set this to 1. And this is what he says about this very special case. (1) 7. We have assumed the phase of the harmonic motion equal to 0. This restriction may be removed by writing the equation of the harmonic motion in the form given here. We created this. When p divides epsilon is a phase of the motion in this form, where p divides epsilon is the phase of the vibration. The equation of the resultant motion then becomes equation 2. This is representing equation 2. And apparently, equation 2 is more general than equation 1. For the former goes over the latter if we put theta as theta prime plus p divides epsilon q. That is, if we turn the initial line through the angle, there is no loss in generality, and the curve is to be considered if we assume the phase of the vibration is equal to 0. Geometrically, what is stated here will be shown here. Remember, the vibration is this smaller circle. The simple harmonic curve is also the vibration. He continues on and comes to this. When generating these curves, you can get many indeterminate forms. Many indeterminate forms. He addresses this right now. Robert Moritz states, "We shall, throughout the remainder of this paper, impose the restriction that Q divides P be rational, and unless otherwise stated, shall use the term cyclic harmonic subject to this restriction." Right there, he says, hey, there's going to be like a ton of curves, right, that like don't make sense. They're just gonna through this way to generate them, right? What may happen, right, as these two poles are spinning, as it is right now, eventually they come back to that same point. He's talking about all the other ones that don't come back and just go to blah. He says, those ones we don't care about right now. And just so as I continue on, remember he wrote a very large book on quotes of other mathematicians. I haven't read it all. I bet he never quotes himself once. If I was to quote him, this is what it would be. Look at that. Okay. It would come from this line here, starting right here. You will soon learn the irony. But the simple mode of generation, which gives rise to all of these curves and that infinite number of others, those ones we don't care about, seems to have escaped the observation of previous investigators. There appears not even a single record of a common class, name, or of any attempt of classification. So likewise, the many beautiful properties common to all of these curves appear never to have been brought to light. For this reason, no doubt, that the special cases which have been carefully studied, these properties are so veiled as to elude detection. We'll continue on there. Pretty much what she's saying is, man, I can't believe it. Like, no one else has wrote about these curves, and I can sum them up in 11 pages. The whole theory that's even remarkable to him. The next couple pages. So the next couple pages, I won't read for word, but he gives the trigonomic to algebraic connection via generated sums. These coefficients are quite amazing. This idea here, I believe to be novel to him. He says this is sort of new method, 1921. It's obvious that the coefficients of the terms in row, the right member of the equation 7, are independent of P. That is, these coefficients are invariant for all cyclic harmonics having the same value of Q. Similarly, the coefficients of the terms in X and Y, the left member, are varying the factor alpha to Q, independent of Q. Hence, these coefficients are invariant for all values of Q. This property greatly facilitates the computation of the Cartesian equations of the various genera of cyclic harmonics. It should be further observed that the computation of the B's, which enter C's, may be expedited. This is original work by him. May be expedited by superimposing one on the other of the two arrays. Any required value of B sub Q minus 2m may then be obtained by adding the products of the superimposed terms. Right? Lay on superimpose, lay on top this, all of these right on top, boom, and then that's like he's talking about the Hadamard product, the pointwise product, this matrix pointwise product, right? He's saying, hey, superimpose, you mean take this element and be it, yes. Now this is quite amazing. This is page 8. He gives this array of numbers that he calculated. And if people that are unfamiliar with discrete calculus, there's the regular calculus, there's integration, and then there's the derivative. And there's e to the x, it's that special function, it's that magical, it's the easiest function in the world. Well, why? Because the derivative of e to the x is e to the x. Well, in the discrete world, that same magical function is 2x. And here is, for the next few minutes, just a quick example of how to do discrete calculus. Quick example of integration and the derivative. So using the first line, we're going to use the sequence. 1, 2, 4, 8, 16. Obviously, they're powers of 2. 2 to the 0, 2 to the 1, 2 to the 2, 2 to the 3, 2 to the 4, and so on. To take the integral, well, this idea of an integration means to take the sum up to that. So if I was going to integrate this, I'd say, well, what is the sum up to this number? Well, it's 1. What is the sum up to this number? It's 2 plus 3. What is the sum up to this number? Well, 3 plus 4. Doop, doop, doop. And so on. Oh, 7. Oh, if I add this 8 on, it becomes 15. 31. 63. Or, in general, if I've got to the 8th number in the 2x sequence, I can say, oh, I bet the sum is probably 255. That would be integrating 2x. Right? And now remember how I said 2x is that magical discrete function because the derivative is always itself. Here it is. Give it the same sequence, 2x, 1, 2, 4. How do you take the derivative? We took the sum for integration, the derivative, take the difference. And I've written the difference right here, 1, 2, 4, which, by the way, is the original sequence. Without just blindly believing me, let's do the math. 2 minus 1, 1. 4 minus 2, 2. 8 minus 4, 4. It returns the original. Like e to the x, what's the derivative? E to the x. What's the discrete derivative of 2x? 2x. Shifted 1 over. So, these two tables, he gives two separate coefficients, right? And he can link them. See this, the 1, 2, 1, 4, 3, 8, 8, 1. Each one of these cells can also be found on this line, on the 2, 1, 4, 3, 8, 8, 1, 16, 25, right? 16, 20, yep, see, okay. OEIS, right? This chain of sequences, right, starting at 1792, 1793, 1794 is well established. This is the generating function for line 1, generating function for line 2, and so on can be found here. Let's look up 1792. Should be 138 something. Let's look it up that way. I said 138 something. Oop. Okay, let's do a few more. Well, we could do a few more, or I could do 1792. Both ways, doesn't matter. I don't want to edit or keep going back and forth because it's going to just, yeah. Or A00 1794. Okay, Chebyshev 1732. Hey, what's the ones was I talking about? Go back here. 1732. 1732. Boop, boop, boop. So, yep. So that is this chain. Moving down here. It's already understood. Each one of these cells can be found here. Well, when looking at this number array, the first thing that came to my mind can be found, and it only works on line 0 and 1. It doesn't work for any other. So then I say, oh, let me look at line 2. or sorry, line numbered 1. It says 1, 4, 12. Well, what could that be? Let me take the sum of 1. Oh, it's 1. 4. Well, let me take the sum of 2 plus 1 plus 1. 12. 4, 6, 10, 12, right, 32. So that's a pattern, but then it fails after that. So here, just starting at what I call 2 sub 1. Right? And I've got this absolute value of the Chebyshev, right, of that number. So starting at 2-1 goes 1, 3, 8, 20, right? Now, looking diagonally, we could find that again as 1, 3, 8, 20, and so on. Notice 2 has 2 subrows. 3 has 2 has 1 subrow. 3 has 1 subrow. Starting at 4, there's 3. And this 8, right? You think of this 8, right? And this 8 are alike. Well, what about this 8? That is also that 8. This is amazing. And he didn't know this. Watch this pattern. 1, 3, 8, 20. We can generate this the same way. 1, 3, 8, 20. Now, inside, okay, 1, 3, 8. 1, 3 something. Moving down, 1, 5, 18, 56. Okay, 1, I said, here, I'll put it in here. I said 1, 5, 18, 56. Let's see. And then it would be, let's see, 18, or 156. Oh, goodness, that's okay. Here, let's go to OEIS. A 53 120. A00, right? 53 120. Probably more than one. Okay, the Chebyshev's periodic table. Powers of 2. 1, remember what I just said? 1, 3, 8, 20. 1, 5, 18, something. And there they are. Take the unsigned values. 1, 7, 32. Good. This interleaved are those. I wrote 63 here because I wondered the same thing. He answers it later on. 2.6. The foregoing table of coefficients enables us to write the Cartesian equation of each of the 63 genera of cyclic harmonic curves for PQ. I like this old symbol. I understand what it means, rarely used today. For P and Q on the 10. Okay. Like it. Is decreasing powers of rho. The degree of the equation in rho is P plus Q. The coefficients could be rho to the P plus Q. And here it is. 2.7. The process of rationalization is exceedingly laborious for all but the lower values of Q. It required several days of intense work on the part of the writer to compute the coefficients in the Cartesian equation, whose equivalent polar form is rho equals alpha cosine 10 divides theta plus a k, written at length, is given here. He says, oh, by the way, but doing all this work, I can also prove that every cyclic harmonic curve in the form this, without k not equals 0, is algebraic of this order. He also notes this: cyclic harmonic curves for which both p and q are odd and k are algebraic curves of order p plus q. Every cyclic harmonic curve is therefore an algebraic curve of even order. Of even order. Here he uses the totient function inside this problem to answer his problem of how many generations. And this is the last page here. This is quite interesting. He says that the cyclic harmonic curves are unipart. I think I said unipartite. It's sufficiently obvious from their definitions that they are also unicursal or rational. That's the key, those two words right there. And when I talked about these can lead to more curves that degrade to nothing than actual curves that lead to something, he gives them a name. They are either rational or unicursal. And here, the Chebyshev polynomial can really be viewed as a product of cosines. And then, so starting off, he says, hey, I'm going to define all these objects, and I need to relate it to something that's already very constructible. Thus, he uses the integer parameterization of the unit circle given by this. Thus saying, he says, hey, I can take some circles, I can map points of those circles to these objects called the cyclic harmonic curves. And these cyclic harmonic curves are either rational or unicursal curves. And that ends his paper. 11 pages. That's the entire theory. I'm saying here, oh, by the way, here's this. He's saying, yes, the circle group can be given well defined. And there's a dual, yeah. And he generated every object by his method. Okay, so now comes the start of the end of the video. Let this axis be theta 1. Let the y-axis be theta 2. Construct a ray as such. I will put a point on that ray. to construct a line segment. Now I have this point and this point. Let's see. Oh, that happens. That's okay like that. There we go. I'm going to notice that point B will move the segment, and C draws the segment. Thus, I could take C. Sorry, not C. I want an additional point. Go. That I will call that one P. Make it a different color. There we go. Some funny point there. Let's see. This point does something different. Let me change that to something different. Okay. So now I got B is going to do that. I want P to go like that. And I can make that segment that P is on as long as I want. Okay, point P. I want to change the scripting and just make it oscillate back and forth. I want the X value P. I want the Y value of P. And I'm going to create an angle. First, put a point at 1, 1, angle with given size. That size is alpha. Sorry, A. Angle with given size again, B. Now, as P moves along, you can see these 2 points move. Let me take the midpoint. Thus, and the locus of E with P, he calls uncursal. This is an uncursal curve. Right? Could be given see, there it is. If I let P be constrained to the ray, I would demonstrate that right now. We confine, we unattach P. P should maybe be by itself. A new ray. Here's a new ray. Let me put that point on it. An uncursal curve. This is integer curve. Uncursal. Thank you very much. The next video covers uncursal curves.